I'm Wil McCarthy, Futuresmith. I'm the author of Rich Man's Sky and other science fiction novels. You can find out more at futuresmith.com. So called hard science fiction is fiction where the science is correct, or at least sounds correct enough to satisfy a demanding audience. In this series, we'll explore how I've used simple calculations in a spreadsheet program to work out technical details for science fiction novels like Rich Man's Sky. Okay, welcome back. Last time we were here, we talked about acceleration in a straight line, and we used Microsoft Excel to calculate the motion of a spaceship accelerating in a straight line at a gentle acceleration of 1 meter per second squared, or 1/10 g. And we found that if we maintained that level of acceleration over 10 days, we could reach 0.3% of the speed of light, which is pretty fast. And we could travel a distance of about 2.5 AU. And AU is the distance between the Earth and the Sun. Um, so 2.5 AU is more than enough to get us to Mars, which is 1.5 AU from the Sun. It's enough to get us to about the middle of the asteroid belt. It's not enough to get us to Jupiter. Um, Now, the problem with all of these things is that if you only accelerate, then by the time you get where you're going very fast. So if we uh, reach Mars, but we're going 0.2% of the speed of light, that doesn't do us a lot of good. Let's see how long it does take us to get to Jupiter if we add a couple of days here. Uh, Now, we've screwed up one of our columns here. Sometimes if you copy a 1 down, Excel thinks that you want a 2 and a 3 beyond that, but we just want ones. That's our acceleration. It doesn't change over time. Uh, and so that's not enough distance. Let's keep going. Uh, Again, with just the ones. So what we find is that on between day 4 and day 15 is when our distance traveled in astronomical units uh, crosses 5. Um, so that's how long it takes to get to Jupiter. Depending on where Jupiter is in its orbit and where Earth is in its orbit, Jupiter could be anywhere from 4 to 6 AU away from us, but we'll just call it 5. Um, what this tells us is it takes about 14 and a half days to get to Jupiter if we don't worry about stopping uh, when we get there. The problem is when we do get there, we're going 0.4% of the speed of light, which is very fast. So what we actually have to do is halfway to Jupiter, we have to turn around and start decelerating uh, so that when we get there, we have a velocity of 0. So let's see what that looks like. Let's take some of these ones and turn them into minus ones. And what we find then is that the first thing that happens is we've screwed up our distance calculation. You can see here our distance traveled in astronomical units has suddenly gone negative. Uh, and that's because the calculation we're using for distance is 1/2 AT squared. That's 1/2 the acceleration times the time squared. Uh, and then this is a conversion unit conversion between meters and astronomical units. So that calculation isn't going to work anymore. What we'll do instead, we have the distance that we travel in AU per day, and we have the distance that we've traveled thus far in AU. So what we'll do is we'll just say this number is equal to that number plus that number. That's an approximation, but it's pretty close. And we'll fill that down. And so what this tells us is that 15 days, if we decelerate uh, on day 11, 15 days is not enough time to reach Jupiter. How long does it take us to reach Jupiter? Well, let's keep traveling. Uh, what this tells us is that about day 18, between day 17 and day 18, is when we reach the orbit of Jupiter. We've got our minus ones messed up again. Uh, so this says on day 18, almost exactly day 18. Uh, Between day 17 and day 18 is where we encounter the orbit of Jupiter. Uh, the problem is we're still not stopped when we get there. We're still going 0.1% of the speed of light. So we need to, uh, this is pretty common sense. We accelerated for 10 days at 1 meter per second squared. To reach a velocity of 0, we're going to have to decelerate for 10 days at that same rate. So if we do that, then we've overshot the orbit of Jupiter slightly. Uh, uh, so this tells us that we need to turn around a little bit earlier. We need to not turn around on day 11. But what happens if we turn around on day 10 is that we reach Jupiter on day 18 with a velocity of 0. Uh, whoops, we still have these distance errors. What happened there? We'll add that to this, and we'll pull that all the way down. And so what we find then, is that if we start decelerating on day 10 instead of day 11, we don't reach Jupiter, where our velocity reaches 0, but we're nowhere near Jupiter when it does. So we, in fact, need to start decelerating on day 11. Sometime between day 10 and day 11 is when we need to turn the ship around and start decelerating if we want to reach Jupiter. And we can calculate this more precisely by putting in 10.5 days, 10.4 days, things like that. But really, it's good enough to know this is all very back of the envelope kind of calculation that uh, between day 10 and day 11 is when we want to turn this ship around. Now, the other thing that you'll notice here, last time we calculated how much fuel we need to make this journey, and we are imagining nature's most perfect fuel, which is antimatter. When antimatter comes in contact with matter, it's converted into pure energy. And we're assuming, for the sake of argument here, that it's converted into pure kinetic energy. There isn't actually an engine that can do that we know of, but we're just trying to get the flavor of how much energy it takes to fly around the solar system at these kinds of speeds. So you'll notice that another error has crept in. Our fuel calculation tells us that we need 4.1 kilograms of matter and antimatter to accelerate for 10 days. And this is just 1/2 mv squared as our kinetic energy. And then to calculate our mass energy that we need to convert for that, it's E equals mc squared, which is a familiar equation, I think, to many of you. And since E equals mc squared, m equals E over c squared, which is what we have here, c being the speed of light, which is 3 times 10 to the 8th meters per second. Now, that's fine. We need 4.1 kilometers of mass to accelerate for 10 days. That's 2 kilometers or 2 kilograms of antimatter and 2 kilograms of matter, which is fine. But as our velocity drops back to 0, our kinetic energy drops to 0. And this tells us that we need 4.1 kilograms of mass to go halfway, and we need 0 kilograms of mass to go the whole way. And that's obviously nonsense. If it takes us 4.1 kilograms to accelerate for 10 days, it also takes us 4.1 kilograms to decelerate for 10 days. So the total amount of fuel that we need to complete this journey is 8.2 kilograms. Now, this is based on mass of our spaceship being 1 million kilograms, which sounds like a lot. It is a lot. It's about the weight of three fully loaded jumbo jets. Um, so heavier than a space shuttle, probably lighter than the Starship Enterprise. Um, but if you want to do these calculations with a lighter spaceship, you can uh, do instead of 10 to the sixth, you can do 10 to the fifth. Uh, and we can copy that up here and see that it takes, oh gosh, a tenth as much mass, which makes sense. Um, but let's undo that. Um, anyway, this is our journey. This is our mission to Jupiter, uh, and you can vary any of these parameters. You can these are all very simple calculations that Microsoft Excel makes very easy to do. Um, so you can calculate your own mission this way. Now, the question of orbital mechanics comes up. People are always talking about doing slingshot orbits around Jupiter or banking around the sun, things like that, and that's fine at lower speeds. When you're going this fast, um, when you're accelerating at 1/10 of a g and you're going 0.3% of the speed of light, uh, the gravity of the planets, the orbital mechanics of your journey are negligible, and you really are basically traveling in a straight line. So you can neglect all of the messy orbital mechanics stuff. We'll talk about that in a future lesson. For now, we're done for today. Please like, follow, and share, and we'll see you next time. Thanks. Bye.